Earlier, we used two data points to estimate the equation for a straight line. Our estimated line will pass exactly through the two data points we used to estimate it. However, it may not agree well with other data points we acquire. Since we never know how accurate any given data point is, it's better to acquire more data points and use all of the data points to estimate a line and minimize the overall error between the line and all of the points. This process is called linear regression or curve fitting. Engineers need mathematical models in order to predict the behavior of systems and perform system design. These models are often estimated from measured input-output data for the system. Earlier, we estimated equations of straight lines from two measured data points, which we assumed would both lie exactly on the line. There are problems with this approach. One of which is that the measurements are always subject to errors and noise, so we can't necessarily trust the individual data points to be completely correct. Another problem is that all systems are nonlinear to some extent, and any linear model will be only an approximation to their actual behavior. Therefore, the best mathematical model may not necessarily pass through all or even any of the data points we measured. What we really want is a straight line model for the data that best describes the overall behavior of the data. For example, in a previous video, when we estimated the straight line equation governing the response of our thermistor from 2 points, the resulting equation didn't agree particularly well with the third data point we measured. It would probably be a better idea to use all 3 data points to generate a straight line equation that has the least overall error among all of the data points. In general, the situation is as shown here. We have a number of measured data points, which are represented as XY combinations. The X values are on the horizontal axis and the Y values are on the vertical axis. Each data point has an X and a Y value. The first data point is at a point specified by X1 and Y1. The second point is at X2, Y2. The kth data point is at X sub k, Y sub k. And the last data point, or the nth point, is at X sub n, Y sub n. Our goal is to use these data points to estimate a mathematical function that best describes them. If we want to use a straight line to approximate the data, we could just use a ruler to draw what we think is the line that best approximates the data. This isn't necessarily a bad approach, but there are some drawbacks. No two engineers are likely to choose exactly the same line, and it's hard to define what exactly we mean by best. Usually it's preferable to define what we mean by best mathematically and then use that approach to create the best fit line to the data. That way everybody knows the rules associated with our choice and our line is unambiguous. In this video, I'll use what's called a least squares best fit of a line to data. The general idea is that we have a set of data points, as in the previous slide, which are represented by XY pairs. X1, Y1, X2, Y2, on up to X sub n, Y sub n. We start out by choosing a shape for the curve we're going to approximate the data with. I'll use a straight line. Now we need to decide how to represent the error between the data and the line representing the data. There are a variety of ways to do this. The approach I'll use here is to use the perpendicular distance between the line and the point. In least squares curve fitting, our error will be the square of that distance. So we'll define the vertical distance between the line and the data point at that value of x as the error in the estimate at that value of x. So the error at x1 is e1, the error at x2 is e2, and the error at the kth data point is e sub k. Since we've chosen to represent the data by a straight line, the equation of the line is y is equal to m times x plus b. So at the kth data point, e sub k is equal to the data value, y sub k, minus the value of the line at that point, which will be m times the value of x sub k minus b. Our goal is going to be to minimize the error by choosing appropriate values of m and b. Now I'll summarize the approach. The first step is to define the error at the data point k, which is the difference between the measured y value and the value of the function given by the curve fit at that data point. That's y sub k minus m times x sub k plus b. Then square this error at each data point and add up all the contributions to get an overall error between all the data points and the curve fit. This symbol, the Greek letter sigma, denotes summation. Finally, choose values of m and b in this equation to minimize this overall error. This step is mathematically kind of tedious, so I'll gloss over the details and just give the result on the next slide. This is our equation for the slope of the line. N is the total number of data points. We multiply that number times the sum of the product of each x value by the corresponding y value. From that, we subtract the sum of all the x values multiplied by the sum of all the y values. The denominator of the equation is n times the sum of all the squares of the x values. Subtract from that the sum of all the x values squared. The equation for the y-intercept is this. In the numerator, I sum all the y values, multiply that by the sum of the squares of all the x values. From that, I subtract the sum of the products of the x values times their corresponding y values times the sum of all the x values. The denominator of this equation is the same as the denominator of this equation. Now let's do an example to see how to apply these equations. These are the 3 data points that I acquired when I used a frying pan to characterize the thermistor's response. The temperatures at which I measured the resistances were 25, 40, and 50 degrees centigrade. The corresponding resistances were 9,700 ohms, 5,000 ohms, and 4,200 ohms. In our equations, we'll need these values as well as the values of the squares of the x's, so 25 squared is 625, and the products of the x and y values, so 25 times 9,700 is 242,500. Now we need the sums of all of these values, which are shown here. So, for example, 25 plus 40 plus 50 is 115. Now I'll use all of these values to calculate the slope of the curve. In this equation, n is equal to 3. I have 3 data points. The sum of the products of the values are here, 652,500, minus the sum of all the x values, which is 115, times the sum of all the y values, which is 18,900. In the denominator, I have n, still 3, times the sum of the squares of the x values, 4,725, minus the sum of all the x values, 115, squared. When I do these calculations, I get m is approximately negative 227.4 ohms per degree centigrade. Now let's do the same thing for the y-intercept. This is my equation for the y-intercept. In the numerator, I have the sum of all the y values, 18,900, times the sum of the squares of the x values, 4,725, minus the sum of the products of the x and y values, 652,500, times the sum of the x values, which is 115. The denominator is n times the sum of the x values squared, 4,725, minus the sum of the x values, 115, squared. When I do this arithmetic, I get b is equal to 15,066 ohms. These circles represent the data points I acquired when I characterized the thermistor in the previous video. Temperature is on the horizontal axis and resistance is on the vertical axis. When I originally estimated the equation governing the thermistor response, I used these two data points. So the line passes through both of those data points. However, there's a fairly large error between the third data point and the line. This line was generated from the least squares best fit using all three data points. The line doesn't agree exactly with any of the data points, but on the other hand, none of the errors at any individual data point are as large as the error at this data point. Another advantage of the least squares fit is that the estimated line is less sensitive to errors in a single data point. If I make a mistake when I'm measuring one of the only 2 points I use in my estimate of the line equation, I might be in big trouble. If I have 10 or 12 or 100 data points and perform a least squares fit using all of the points, an error in a single data point won't have as much of an effect on the final result. Here's an example. Suppose I have the data point shown here. This data point is obviously an outlier. It's probably the result of an error in the test. If I use only 2 points to estimate my line, and if I'm unlucky enough to pick these 2 points, I'll get a line that doesn't really agree with the data very well at all. Even worse, if I only have these 2 data points, I don't get anything even remotely like the trend that's in the overall data set. However, if I use all of the data points and perform a least squares best fit, the effects of the one bad data point are diminished relative to the other points, and I get a very reasonable approximation to the overall data set. The calculations necessary to do line fitting aren't difficult, but they are tedious and prone to arithmetic errors, especially if there are lots of data points involved. The process wasn't too bad for 3 data points. But if you have a few hundred or 1,000 points, you're not going to want to do these calculations by hand. Therefore, some software packages have built-in functions to perform least squares curve fitting. A few of the most popular ones are MATLAB, Excel, Octave, and Scilab. MATLAB and Excel you have to buy, while Octave and Scilab are free software packages that emulate MATLAB's capabilities. It's worth mentioning that these software packages don't directly use the equations I've given you in this video. Our equations are prone to round-off errors, which are a result of any computation performed by a computer. However, the results of the computer software packages will be the same as the results you get with our equations. The moral of this video is that even though you can estimate a straight line from 2 data points, it's better to acquire more data points and curve fit the line. This increases your confidence that the model's behavior replicates the overall behavior of the system, even if the model no longer predicts any of the individual points exactly.